Not all transformers are isolation type. Isolation transformers provide galvanic isolation between the primary and secondary windings. This means there's no direct electrical connection between them. Autotransformers, on the other hand, have a single winding that serves as both the primary and secondary windings, creating an electrical connection between the two circuits. For this application, which involves feeding a UPS main bypass panel, an isolation transformer is specifically needed. This is crucial because the UPS must be galvanically isolated from the utility power supply. This isolation prevents ground loops and other electrical hazards that can arise from direct electrical connections. The specific transformer requirements for this setup include a primary voltage of 480 volts and a secondary voltage of 208/120 Y volts. The power rating should be 225 kVA. The transformer needs to be capable of handling 800 amps at 208 volts, which is the required current for the bypass panel. And to reiterate, an isolation-type transformer is essential. Beyond these specifications, several additional considerations are important. Firstly, always ensure that the transformer meets all applicable electrical codes and standards. This is a non-negotiable requirement for safety and compliance. Secondly, carefully consider the physical space and weight of the transformer when planning the installation. Transformers, especially those of this size, can be quite large and heavy, so proper planning is critical. Thirdly, it is strongly advised to contact a qualified electrician for proper installation and maintenance. Working with high-voltage equipment is inherently dangerous, and a trained professional will have the knowledge and experience to ensure the installation is done safely and correctly. Delving deeper into the technical aspects of isolation transformers, it's important to understand how they achieve galvanic isolation. The primary and secondary windings are physically separated and electrically insulated from each other. This separation is typically achieved using insulating materials like varnish, paper, or epoxy resin. The amount of insulation between the windings determines the isolation voltage rating of the transformer. This rating indicates the maximum voltage that can be safely applied between the primary and secondary windings without risking electrical breakdown. The benefits of using an isolation transformer extend beyond just preventing ground loops. They also help to reduce electrical noise and improve power quality. This is because the isolation transformer acts as a barrier to common mode noise, which is a type of electrical interference that can be present on both the hot and neutral conductors. By blocking this noise, the isolation transformer can help to ensure that the UPS receives a clean and stable power supply. This is particularly important for sensitive electronic equipment that is susceptible to damage from electrical noise. The selection of an appropriate isolation transformer also involves considering the transformer's impedance. Impedance is a measure of the opposition to the flow of alternating current. A transformer's impedance affects the voltage regulation of the system. Voltage regulation refers to the ability of the transformer to maintain a constant secondary voltage under varying load conditions. A transformer with low impedance will have better voltage regulation than a transformer with high impedance. However, a transformer with low impedance will also have a higher inrush current when it is first energized. Inrush current is the large surge of current that flows into a transformer when it is initially turned on. This inrush current can be several times the transformer's rated current, and it can potentially damage the transformer or other equipment in the system. Therefore, it's important to select a transformer with an impedance that is appropriate for the application. The type of core material used in the transformer also affects its performance. Common core materials include silicon steel and amorphous metal. Silicon steel is a relatively inexpensive core material that is widely used in transformers. Amorphous metal is a more expensive core material that offers improved performance characteristics. Transformers with amorphous metal cores have lower losses and higher efficiency than transformers with silicon steel cores. This can result in significant energy savings over the life of the transformer. Another important consideration is the transformer's cooling method. Transformers generate heat as they operate, and this heat must be dissipated to prevent the transformer from overheating. Common cooling methods include air cooling and liquid cooling. Air-cooled transformers rely on natural convection or forced air to dissipate heat. Liquid-cooled transformers use a liquid coolant, such as oil or synthetic fluid, to transfer heat away from the transformer. Liquid-cooled transformers are typically more expensive than air-cooled transformers, but they offer better cooling performance and are often used in high-power applications. When selecting a transformer, it's also important to consider its efficiency. Transformer efficiency is the ratio of the output power to the input power. A more efficient transformer will waste less energy and generate less heat. Transformer efficiency is typically expressed as a percentage. For example, a transformer with an efficiency of 98% will convert 98% of the input power into output power, with the remaining 2% being lost as heat. The location where the transformer will be installed is another important consideration. If the transformer will be installed in a harsh environment, such as a dusty or corrosive environment, it's important to select a transformer that is designed to withstand those conditions. This may involve selecting a transformer with a special enclosure or coating. The altitude at which the transformer will be installed can also affect its performance. At higher altitudes, the air is thinner, which reduces the cooling capacity of air-cooled transformers. Therefore, it may be necessary to direct the transformer's power rating if it will be installed at a high altitude. Finally, it's important to properly protect the transformer from overcurrents and other faults. This can be achieved by using fuses or circuit breakers. The protective devices should be sized appropriately to protect the transformer without nuisance tripping. In summary, selecting the right isolation transformer for a UPS system involves careful consideration of various factors, including voltage, power, current, isolation type, electrical codes and standards, physical space, weight, impedance, core material, cooling method, efficiency, environmental conditions, altitude, and protection. Consulting with a qualified electrician is highly recommended to ensure that the transformer is properly selected and installed. Focusing more specifically on the 225 kVA transformer mentioned, it's useful to contextualize its capacity within typical industrial or commercial settings. A 225 kVA transformer is often used to supply power to medium-sized commercial buildings, small industrial facilities, or large data centers. It's capable of handling a significant electrical load, but it's also important to understand its limitations. The 225 kVA rating represents the transformer's apparent power capacity. Apparent power is the product of voltage and current, and it's measured in kilovolt amps. The actual power that the transformer can deliver depends on the power factor of the load. Power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the power is being used effectively, while a power factor of less than 1 indicates that some of the power is being wasted. Most electrical loads have a power factor of less than 1. For example, electric motors typically have a power factor of around 0.8. This means that a 225 kVA transformer can only deliver about 180 kilowatts of actual power to a motor load. It's also important to consider the transformer's duty cycle. Duty cycle refers to the amount of time that the transformer is operating at its rated load. A transformer that is operating continuously at its rated load will generate more heat than a transformer that is operating intermittently. Therefore, it may be necessary to direct the transformer's power rating if it will be operating continuously at its rated load. In addition to the factors already mentioned, there are several other technical considerations that are relevant to selecting an isolation transformer for a UPS system. These include the transformer's harmonic distortion, transient voltage suppression, and common mode noise attenuation. Harmonic distortion refers to the presence of unwanted harmonics in the electrical waveform. Harmonics are multiples of the fundamental frequency of the power system, which is typically 60 Hz in the United States. Harmonics can be generated by nonlinear loads such as electronic devices and adjustable speed drives. Harmonics can cause a variety of problems, including overheating of equipment, increased energy consumption, and interference with communication systems. Isolation transformers can help to reduce harmonic distortion by blocking the flow of harmonic currents. Transient voltage suppression refers to the ability of the transformer to protect sensitive equipment from voltage spikes and surges. Voltage spikes and surges can be caused by lightning strikes, switching operations, and other events. These voltage transients can damage or destroy electronic equipment. Isolation transformers can help to suppress voltage transients by providing a high impedance path to ground. Common mode noise attenuation refers to the ability of the transformer to reduce common mode noise. Common mode noise is a type of electrical noise that is present on both the hot and neutral conductors. Common mode noise can be caused by a variety of sources, including radio frequency interference, electromagnetic interference, and ground loops. Common mode noise can interfere with the operation of sensitive electronic equipment. Isolation transformers can help to attenuate common mode noise by providing a barrier to the flow of common mode currents. When specifying an isolation transformer for a UPS system, it's important to consider all of these technical factors. The specific requirements will depend on the application and the sensitivity of the equipment being protected. Consulting with a qualified electrical engineer is recommended to ensure that the transformer is properly specified and installed. Going into even greater detail about the voltage considerations, the 480 volts primary to 208/120 volt secondary configuration is a very common setup in North America. The 480 volts is a standard voltage for industrial and commercial power distribution, while the 208/120 volts is a standard voltage for general purpose lighting and receptacle circuits. The Y in 208/120 refers to a Y-connected secondary winding. A Y-connected winding has a neutral point that is connected to ground. This provides a stable and safe voltage for single-phase loads. The 208 volts is the voltage between any two-phase conductors, while the 120 volts is the voltage between any phased conductor and the neutral conductor. The 120 volts is the voltage that is typically used for lighting and receptacle circuits. When connecting loads to a 208/120 volt system, it's important to balance the load across the three phases. This means that the load on each phase should be approximately equal. Unbalanced loads can cause voltage imbalances and other problems. Voltage imbalances can lead to overheating of equipment, reduced motor life, and increased energy consumption. It's also important to properly ground the neutral conductor of the 208/120 volt system. This provides a low impedance path for fault currents to flow back to the source. A properly grounded system will help to protect people and equipment from electrical shock hazards. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. Article 250 of the NEC covers grounding and bonding requirements. It's important to follow the NEC requirements when installing and maintaining a 208/120 volt system. In addition to the voltage and grounding requirements, it's also important to consider the overcurrent protection requirements for the transformer. The NEC requires that transformers be protected from overcurrents by fuses or circuit breakers. The overcurrent protective devices should be sized appropriately to protect the transformer without nuisance tripping. The NEC provides specific requirements for sizing overcurrent protective devices for transformers. These requirements are found in Article 450 of the NEC. It's important to follow the NEC requirements when sizing overcurrent protective devices for transformers. Considering the ambient temperature is also important. The ambient temperature is the temperature of the air surrounding the transformer. The transformer's power rating is based on a specific ambient temperature, typically 40 degrees Celsius. If the transformer will be installed in an environment with a higher ambient temperature, it may be necessary to direct the transformer's power rating. This means that the transformer will not be able to deliver its full rated power without overheating. The transformer manufacturer can provide information on how to direct the transformer's power rating for different ambient temperatures. In cold environments, condensation can form inside the transformer. Condensation can damage the transformer windings and insulation. To prevent condensation, it may be necessary to install a space heater inside the transformer enclosure. The space heater will keep the transformer warm and dry, preventing condensation from forming. Transformers can also be affected by vibration. Vibration can loosen connections and damage the transformer windings. If the transformer will be installed in an environment with high vibration, it may be necessary to use vibration isolators to protect the transformer. Vibration isolators are devices that are designed to absorb vibration and prevent it from being transmitted to the transformer. Finally, regular maintenance is essential for ensuring the long life and reliable operation of the transformer. Regular maintenance should include inspecting the transformer for damage, cleaning the transformer, and testing the transformer's insulation resistance. The transformer manufacturer can provide recommendations for regular maintenance procedures. Another crucial aspect when dealing with isolation transformers, especially in UPS applications, is understanding the impact of nonlinear loads. Modern electronic devices, such as computers, servers, and LED lighting, often draw current in a non-sinusoidal manner. This non-sinusoidal current waveform introduces harmonic distortion into the power system. Harmonic distortion can lead to a variety of problems, including overheating of transformers, increased neutral currents, and interference with sensitive electronic equipment. Isolation transformers can help to mitigate the effects of harmonic distortion by blocking the flow of harmonic currents between the primary and secondary windings. However, it's important to select an isolation transformer that is specifically designed to handle nonlinear loads. These transformers typically have a higher K-factor rating. The K-factor is a measure of the transformer's ability to withstand harmonic current. A higher K-factor rating indicates that the transformer is better able to handle harmonic currents without overheating. When selecting an isolation transformer for a UPS system that will be supplying power to nonlinear loads, it's important to consult with a qualified electrical engineer to determine the appropriate K-factor rating. Ignoring this consideration can lead to premature transformer failure and other problems. Regarding specific standards and codes, the installation and operation of transformers are governed by a variety of standards and codes. In the United States, the National Electrical Code, or NEC, is the primary standard for electrical installations. The NEC provides detailed requirements for the installation, wiring, and protection of transformers. In addition to the NEC, there are also various industry standards that apply to transformers. These standards are developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards cover a wide range of topics, including transformer design, performance testing, and safety. Some of the relevant IEE standards for transformers include IEC 57.12.0, which covers general requirements for liquid immersed distribution, power, and regulating transformers, and IEC 57.12.9T, which covers test code for liquid immersed distribution, power, and regulating transformers. NEMA also publishes various standards for transformers, including NEMA SD20, which covers dry-type transformers for general applications. It's important to be familiar with these standards and codes when working with transformers. Failure to comply with these standards and codes can result in safety hazards, equipment damage, and legal liabilities. Electrical inspectors will typically verify compliance with these standards and codes during inspections. Furthermore, the grounding and bonding practices for isolation transformers are critical for safety and proper operation. The NEC provides specific guidelines for grounding and bonding transformers in Article 250. A key principle is to ensure that the transformer's secondary neutral point is properly grounded. This grounding provides a low impedance path for fault currents, which helps to protect people and equipment from electrical shock hazards. The grounding conductor must be sized appropriately based on the size of the transformer's secondary conductors. In addition to grounding the neutral point, it's also important to bond the transformer enclosure to the building's grounding system. This bonding helps to ensure that the enclosure is at the same potential as the ground, which reduces the risk of electrical shock. The bonding conductor must also be sized appropriately based on the size of the transformer's secondary conductors. Improper grounding and bonding practices can create dangerous situations, such as ground loops and elevated touch potentials. Ground loops can cause unwanted currents to flow through the grounding system, which can interfere with sensitive electronic equipment. Elevated touch potentials can create a shock hazard if someone comes into contact with the transformer enclosure. Therefore, it's essential to follow the NEC grounding and bonding requirements carefully. Detailing the importance of regular inspections and maintenance. Transformers are robust pieces of equipment, but they require regular inspections and maintenance to ensure their long life and reliable operation. The frequency of inspections and maintenance will depend on the transformer's operating environment and load conditions. However, as a general guideline, transformers should be inspected at least annually. During an inspection, the following items should be checked. Firstly, look for any signs of damage, such as cracks, leaks, or corrosion. Secondly, check the transformer's oil level if it's a liquid-filled transformer. Thirdly, inspect the transformer's bushings and connections for signs of overheating or looseness. Fourthly, test the transformer's insulation resistance to ensure that the insulation is in good condition. Fifthly, check the transformer's cooling system to ensure that it's functioning properly. In addition to inspections, transformers also require periodic maintenance. Maintenance tasks may include firstly, cleaning the transformer's bushings and connections. Secondly, tightening any loose connections. Thirdly, replacing any damaged components. Fourthly, testing the transformer's oil, if it's a liquid-filled transformer. Fifthly, filtering or replacing the transformer's oil, if necessary. Proper maintenance can help to prevent transformer failures and extend the transformer's lifespan. Transformer failures can be costly and disruptive, so it's important to invest in regular maintenance. Finally, it is important to consider the environmental impact. Transformers consume energy and can contribute to greenhouse gas emissions. When selecting a transformer, it's important to consider its efficiency and environmental impact. High-efficiency transformers can help to reduce energy consumption and greenhouse gas emissions. There are also various environmental regulations that apply to transformers. For example, some regulations restrict the use of certain types of insulating fluids that are harmful to the environment. It's important to be aware of these regulations and to comply with them. Additionally, consider the end-of-life disposal. When a transformer reaches the end of its useful life, it must be disposed of properly. Transformers contain materials that can be harmful to the environment, such as oil and heavy metals. These materials must be handled and disposed of in accordance with environmental regulations. Recycling transformers is a good way to reduce their environmental impact. Many transformer manufacturers offer recycling programs for their products. By recycling transformers, the valuable materials can be recovered and reused, which reduces the need to mine new materials. Ultimately, choosing the correct isolation transformer for a UPS system connected to an 800 amp main bypass panel necessitates a comprehensive evaluation. This involves not only matching voltage, power, and current specifications, but also a deep dive into isolation requirements, adherence to electrical codes, and the consideration of environmental elements. Selecting an isolation transformer that complies with standards like the NEC and IEE alongside regular maintenance contributes to a dependable, safe, and environmentally responsible power system.